So last time we have discussed the canonical questions. That's okay. So we have discussed the canonical ensemble. It describes systems whose macroscopic state is described by a system with n particles in a volume V and in equilibrium at a temperature T with a much larger system. And so what we have seen is that if the system has a certain number of states with energy ER, then and if we consider an ensemble of n copies of a system, such a system in this macroscopic state, then we can ask what is the number of copies of the system in this ensemble that we expect to find in a particular state R. And what we have found is that this number nr is e to the minus beta times the energy ER divided by sum over R e to the minus beta times ER. Right? Okay. Now, okay, so this is the number which we expect to find on average if we take a very large number of copies. Sorry, this will be proportional to n. So this factor here is the fraction of copies of the ensemble which will be in the state R. And of course, one thing you may want to be interested in is to understand how much in a particular ensemble this number will fluctuate. How many more copies of the ensemble or how many less copies of the ensemble will be in this system here, okay? In this state here. Now, in order to do that, so what we have seen is that essentially the way in which there is a trick to compute this number here, which is essentially to compute a function, compute an object which is the sum over all the states R of omega R to the nr, sorry, it's the product over all the R of n factorial omega R to the nr to the nr factorial. And where I also take a sum over all the possible distribution of occupation of copies. I take a sum over all possible distribution of this copy over the states, such that the total number of copies is NR, and the average energy in the ensemble is fixed to U. And this is essentially the number of ways in which I can distribute this number of copies, corrected by this factor, which is omega r to the nr. Okay. And the trick is that if you now take derivatives of the logarithm of this function, and compute these derivatives where all the omegas are equal to 1, what happens is that you have exactly the quantity which you want, because every time you take a derivative with respect to omega r, there is an nr which gets out, and you have omega r to the nr minus 1. So when you multiply again by nr, you get again nr times omega r to the nr. And when you do the derivative of the logarithm, you will have at the denominator this term here, which is computed in omega equal to 1, and at the numerator the same sum, but with an nr here. So this will give you the average number of copies in your ensemble which are in state R. Okay. Now there is so the other question, which one the other question which one is interested in is to understand what are the fluctuations. So what are the fluctuations of the number of copies in the ensemble? In particular, say how this gives you a measure of how different occupation of the states you expect to have in different realization of these ensembles. And there is another trick which you can use, which is similar to this, and which is a trick which we will use other times, which is if you want to compute this thing, which is nr squared, the average over nr squared minus the average of nr squared, then what you can do is to take two derivatives of the log of gamma, and then compute this when the gammas are equal to 1. And why is this? Because essentially when you take one derivative, essentially what you have is 1 over gamma times above you have the sum over all the possible occupation numbers. And then the product over all the r of n factorial, n factorial times the product over all the r of omega r nr divided by n factorial. This is exactly what you have here. But then when I take the derivative, I have, as I told you, nr times omega r to the nr minus 1 times the omega r. I just have nr, a factor of nr which comes down. Okay. Okay. So this is what I wrote here is just the derivative of gamma with respect to omega r times omega r. Okay. Now, what happens if you take a second derivative? If you take a second derivative and you multiply by omega r, what you have is that you can take the second derivative up here, and then the effect will be that you have another factor of nr which comes down, and you will get essentially this sum over all the possible occupation with an nr squared. So this will give you, divided by gamma, this will give you the average of nr squared. Okay? And the other way, the other place where you can take the derivative is here. If you take the derivative here, you will have, so the first term will give you nr squared. And if you take the derivative here, you will have, I mean, the exactly minus gamma squared times another factor like this. Okay? So what you will have is exactly nr average squared. Okay? Now, what I'm not going to do this calculation here, but what you, I mean, this is done in the book, in the lecture notes which you have, and it's just it's an exercise for you to understand whether you have understood properly what is the main idea. I mean, the important thing is that what you find is that the relative fluctuation squared of the number of copies in your system which are in state R, you find that this is proportional to 1 over the number of copies which are in this state, plus quantities which go as 1 over the number of copies. So when the number of copies in your ensemble go to infinity, then you see both these terms and also this term will go to 0, which tells you that the relative fluctuations in relative terms, the fluctuations in the occupation number of over the energy levels will be very, very small. Okay. This tells you that if you really take an ensemble, the fraction of system, or the probability that you will find a system in a particular state in different ensembles of many copies, will essentially always be given by this factor here. Okay. Okay, so now we have so we have found a way to so I hope I convinced you that for a system which is in equilibrium with another system at a certain temperature, we have seen that the probability to find the system in a particular state R is given by e to the minus beta times R times normalization function, and times the normalization. And now again, we would like to find, we would like to understand two things. First, what is beta? And then how can we extract physics or thermodynamics out of this distribution? Okay. Now I remind you that beta is fixed in such a way, so beta is such that if you compute the average energy over this distribution, then this is the energy of your system. Okay. Okay, which was fixed. Now, and there is a way in which you can write this relation here, which is interesting, which is you can write it as that the energy is minus the derivative with respect to beta of the log of this sum here. Okay, so this is interesting because we can relate it with thermodynamic relations. So in a system which is under this condition at an equilibrium at temperature T, the thermodynamics is given by the Helmholtz free energy. Okay? Helmholtz free energy, so this is thermodynamics. The Helmholtz free energy is a function of N, P, and T, is the energy minus T times the entropy. Okay? And indeed, the differential of this function here is the differential of u minus T ds minus S dt. But we know that du, by the first law of thermodynamics, is equal to T ds minus P dv, well, plus mu dn, minus T ds minus S dt. So you see that this term and this term cancel. So you really see that the differential of A is a linear combination of the differential of number of particles, volume, and temperature. So this tells you that A is really a function of number of particles, volume, and temperature. Okay, and this also tells you that if you want to compute the entropy will be minus the derivative. So the entropy will be minus the derivative of A with respect to temperature at constant N and B. Okay. Now with this, we can compute and likewise you can compute the other quantities. So with this, we can compute the average energy and compare it to this formula. So the average energy is A plus Ts from this relation here. So is A minus T times dA dt. I'm always considering the N and B are finite, so I'm not writing it. And now there is one way in which I can write this, which is minus the derivative of A divided by T the derivative of a divided by t by 1 over t. Okay, and so why is this so? Because this I can write it as derivative with respect to 1 over t of t times the derivative with respect to t of a divided by t. And well, the derivative of t by 1 over t is t squared, is minus t squared, so this is t squared. And then so yes, there is a plus here. And then, so there is a plus here, so there is a minus t squared times, and then the derivative of a over t with respect to t is 1 over t times the derivative of a with respect to t, and then the derivative of 1 over t with respect to t is just minus 1 over t squared times a. So you see that this gives you exactly this, okay? Now, now you can compare this with this and make, and this tells you that if you make the identification that a is equal to minus t times the log of this object, and that 1 over well, you should have k times t, and that t is equal to 1 over k times beta. Then you see that if you make this identification, then this equation becomes equal to this equation. Okay. Sorry? Well, you say here in thermodynamics, u is the derivative of a function of a over t with respect to a variable which is related to the temperature. Okay. Here also the energy is a derivative of something with respect to another variable. Okay. So I'm just identifying the function here with 1 over I'm just identifying this function here minus the log of this with a divided by t. And so, yes, there should not be any k here. So this is just saying that a divided by t is equal to the log of this, okay? And then that beta, or if you want beta, is equal 1 over kt, so that this so probably I should put the k back. Yeah. Yes. Sorry. 1 over kt. So if I put a k here and a k here, then you see that I can identify these two things. Okay. So this is the key equation in the canonical ensemble. So, so the key, if you want to compute the physical properties of a system at constant temperature and volume, the number of particles, so what you should do is to compute this sum here, the sum over the state of e to the minus beta times ER. And then if you take the log and multiply by kt and change sign, you will have the Helmholtz free energy. And this beta should be interpreted as 1 over k times the temperature. Okay? Sorry? We can also add an arbitrary constant in the sense that you can also add here an arbitrary constant. But well, the other thing, now you can ask yourself, well, imagine now that we do some work on the system, okay? We change, so this constant this constant should not depend on temperature, right? Okay. Now, however, this constant could depend on volume, okay? Now, however, this, so imagine that now I want to make I want to change the volume. I want to do a transformation where I change the volume. So if I change the volume, then from thermodynamics, I know that the change of Helmholtz free energy with respect to the volume, constant n and T, will give me the pressure. Okay. Now, what will happen physically if I change the volume of my system? Okay. So what will happen physically is that the energy levels of the system will change. Okay. So think of the spacing between the different levels will change, and so the change. So if my energy is given by this thing, the change in the energy will be given by the average of the change in the energy levels divided by V. Okay, so this is because I'm making some work on the system, so I'm changing the energy levels. Okay, so you see, if you take the derivative of V with respect to this factor, this is exactly what you will get. So you will get that the change if you write the energy as minus the derivative with respect to beta of the log of sum over R of E minus beta ER. And you know that beta is related to the temperature, so you are doing a change of volume at a constant temperature. Then the change in the energy. So so we know that the change in the energy must be S dt minus P dV. Okay, but dt is constant. Okay, so this must be minus P dV. Okay, and from this equation here, you see that when you make a change in the volume, then your energy levels will change into the initial energy levels plus dr dv times dv, right? And as a result, the change in the sorry? Sorry? Oh, yes. Yeah. Okay. So du is dA plus okay. Yes, so, sorry. If you want to compute the pressure would be minus the derivative of A with respect to the volume at constant n mv. So if I use this relation, then I have kT times the sum over R e to the minus beta er times, here I have the sum over r, and then minus beta times the derivative of the energy levels by v e to the minus beta er. Okay, so and then there is this term minus d a0 dt or dv. Now, what I want to show is that this cannot depend on a0. This a0 cannot depend on v, so this term must be equal to 0. Okay. So the idea is that when I change the volume, say what this formula is telling me is that what changes in my system are the energy levels. So this is just a sum over r dr dv times e to the minus beta er divided by sum over r e to the minus beta er. So when I and this is exactly what you expect when you do some work on the system. Okay, when you do some when you exert some work on the system, you are changing the energy levels, and so if you want to compute the work which has been done by the system, so that then this will be PdV, and this is exactly the amount of deformation deformation which you have done on the energy levels. Okay, so this term cannot be must be 0. Is this clear? So if you want to that this formula here describes correctly thermodynamics, then this constant here cannot depend on temperature and volume. Okay, because this is so if you yeah, no, in this case there is a minus sign here. Sorry, am I missing something? So there is a minus sign here. Okay, yes, you're right, yes. Okay. So there is a plus, there is a minus. Okay. Yes, you're right. And the change in the energy is minus PdV. So so the other thing which the other interesting thing is let us compute the entropy. So if one way to compute the entropy is say that S over K must be equal to beta times U minus the energy minus the minus A, right, from this relation. And now beta times U is the sum over R of beta ER, e to the minus beta ER, divided by sum over R to the minus beta ER. Whereas minus beta times A is just this log of this sum, okay, with a plus. Now, if you call, if you recall that the probability of a state R is equal to e to the minus beta ER over sum over R e to the minus beta ER, what you can see is that this formula is equal to minus sum over R PR log of PR. And so this is a very important formula, which expresses which tells you that the entropy is only a function of the probability distribution. So have you already seen this formula? So this formula is is a formula which is given, which tells you that the entropy is only a function of the probability distribution, and sometimes this is called Shannon entropy. Okay. By the name of a mathematician called Shannon, which used this formula to discuss problems related to information theory. Okay. Indeed, you see this. If you want, when you have a probability distribution, you have some uncertainty. The probability distribution describes some uncertainty. And this formula quantify the uncertainty which is contained in a particular probability distribution in a very specific manner. Okay, and so, for example, you see, well, in our case, this uncertainty is the uncertainty which we have on the microstate of the system, given that we know the macro state of the system, right? So, a particular macrostate can correspond to many microstates. Each of these microstates has a certain probability. And so the entropy characterizes this uncertainty. Okay, so for example, if you consider the particular case where, say, for example, the probability on the states is 1 on a particular state and is 0 else on all the other states. So where this probability is just a delta function on some state, then you see that this corresponds to entropy which is equal to 0. Okay, so in that case, what this tells you is that if you know the macro state, you know the micro state. There is no uncertainty. Okay. So there is only one microstate which corresponds to that macro state. And this is typically what happens at very low temperature, in particular at zero temperature. For a quantum system, quantum confined system will go to if it is a non-degenerate ground state, it will go to one single state. So you expect your probability distribution will be concentrated on only one state. Okay. The other extreme is where you have your probability distribution is if there are a certain number omega of states which are possible. The maximal possible uncertainty which you can have is just that they all have the same probability. This is the maximal possible uncertainty which you have. And in this case, you see that the entropy, in this case the entropy over K, if you use this formula, is minus sum over all the states, say from 1 to big omega, 1 over omega of log 1 over omega. Okay? So this is a constant, you can take it out, and this sum just gives you a factor omega. So what you get is that this sum is just log of omega. So you see, in that case, this formula for the entropy precisely gives you the formula which we have used for the entropy in the microcanonical ensemble. Okay? So this formula for the entropy is very, very important, and is say you could also derive all of thermodynamics just from this formula. For example, imagine that you could just ask yourself, yeah. In the first example, here, yes. Yes.
Now, the entropy is zero in the answer. The entropy is zero in both cases.
Yes. So yes, I'm saying that 0 log 0 is equal to 0. Okay. So indeed, what is true is that if you take the limit as x goes to 0 of x log x, this is equal to 0, right? And of course, so in this case here, you will have one term where r is equal to r star, where you have 1 times log of 1, which is 0. And all the other terms where you have 0 log of 0, and then it is 0. Okay, is this clear? Because essentially, so if you plot this function, you will see that this is a function which is which actually goes to 0, but in a very well, actually, minus this, no? Goes to 0, x log x. It goes to 0, but with an infinite slope. Okay, so, but the limit is 0, so that is why we define that 0 log 0 is equal to 0. Okay. Uncertainty. Okay. So I'm saying, okay. So this is a general question. So imagine that I pose you the following question. So in this case, I mean, for statistical physics, uncertainty for me is uncertainty on the microscopic state. Okay, so I tell you, you measure a physical system. It has this many number of particles, this volume, this temperature, or this energy. It has this macroscopic state. And I ask you, tell me what is the microscopic state? What are the position of particles? And of course, maybe you can measure the position of all the particles, and you can give me an answer. Okay. Now, how much? Of course, before reading your answer, I'm uncertain on what possible state this can be. Okay, so that you see that the more I am uncertain, the more your answer gives me information. Okay, so that you see this is a way to measure. So before that you give me an answer, what I can measure is only the probability of different answers. After you give me the answer, I know the answer. Okay, so this tells me how much information your answer contains, because this is the how much uncertainty I get rid of by listening to your answer. Okay. Now, so when I can figure out a priori that there is only one possible answer, which is this case, your answer will give me no information, okay? Because I can figure out myself. I don't even need to ask you, okay? When instead a priori all the possible answers, there are omega possible answers, and they are all equally probable for me, then this is the case where your answer will give me more information, and this is the amount of information. So this is another way in which you can really make a relation between information and this formula here. So imagine, this is a side remark, okay? So imagine that there is a, imagine there are two people, they are talking to each other, and they are talking about some event, okay? And this event can have a finite number of outcomes, okay? So you want to give a quantitative measure of information, okay? So say there is Mr. A and Mr. B, okay? Mr. A only knows a probability distribution on the outcomes, and Mr. B knows the right outcome, okay? And this R can be from 1 to omega. Okay? Now, one way to say to quantify information is to say how many, imagine that A makes to be a set of binary answers. I mean, there are games like this, no, where you say, is it this or is it that? I mean, and B has to answer yes or no. Okay, yes or no. Then you can say that. So this formula tells you, if you take a logarithm of 2, tells you exactly what is the minimal number of binary answers that A should do to B in order to understand what the correct answer is. So let's do a very simple example where you have all 4 possible outcomes, okay? And they all have the same probability, okay? In this case, A can answer a first question. Is it AB or is it CD? Okay, and then he can answer a second question. If it is AB, then he can answer whether it is A or it is B. If it is CD, then he may ask whether it is C or it is D. Okay, so you need, in this case, A needs to make two questions. 2 consecutive questions, and with 2 consecutive questions, it will know what the outcome is. So you can say that the uncertainty here is 2 bits, because a binary outcome, yes or no, is a bit. Okay? Actually, you could say that this is 0, this is 1, this is 0, this is 1, so this is 0, 0, this is 0, 1, this is 1, 0, and 1, 1. So 2 bits. Now, of course, this is, and you can imagine now that there are 2 to the n. There are 8 possible. There are 8 possible outcomes. Then you can do the same, but you see that you will need a third question. Okay. You can first divide into 2, then for each answer of the first question, divide into 2. Then for each answer of the second question, divide it into 2. And after 3 questions, you will get the answer. So you see that in this case, the entropy is exactly given by this, because it's exactly log 2 of 8, which is 3. Okay. Now, you can convince yourself that this is actually the right way to. I mean, what Shannon has done, Claude Shannon, is to prove a theorem which tells you that this is the minimal number of binary answers which you have to make in order to dispel this uncertainty, okay? In order to figure out what is the outcome of an experiment which a priori has a certain probability distribution R, okay? So, for example, I mean, just to give you a feeling of, so imagine that you know that the probability distribution is 1/2, 1/4, 1/8, 1/8. Okay, so this is A, B, C, and D. So that A is more probable than B, and B is more probable than C and D. Okay. Now you see, if you compute the entropy, in this case you will have minus with log 2. You will get say 1/2 times 1 log of base 2 of 2 is 1. Base 2. I'm using base 2 now. Okay. Then plus 1/4 times 2 plus 2 times 1/8 times the log of 8, which is 3. You see that in this case, the entropy of this distribution would be in base 2 would be 1 plus 3/4 is 7 over 4. Okay. So 7 over 4 is less than 2. Okay. Which means there is a way to pose this question where you need less than two questions, than two binary questions. And you can figure out that, well, indeed, it is better to ask first, it is A or is it not A? And then to ask whether, if it is not A, to ask it is B or it is not B. And if it is not B, to ask whether it is C or D. So it is better to pose questions in this way. It is A or not A. And then if it is not A, it is B or it is not B. And it is, in this case, if it is not B, it is C or it is D. Okay? Now you see, half of the time you will only need one bit. In 1/4 of the time, you will only need 2 bits, 2 questions. And in the most unlucky case, 1/4 of the time, you will need 3 questions. So if you average the number of questions, if you take the expected number of questions which you have to do, it is exactly equal to the entropy. Okay? So the entropy is really related to information and to uncertainty. Okay? Okay, so let's go back to this, to physics. So one thing you can, for example, see is that if you just take this as a definition of entropy and uncertainty, then you can ask yourself, what are the states of maximal? Well, you can ask yourself, what are the states of maximal entropy, which are consistent with the energy being a certain given value. So if you know that you have omega these many states which are consistent with the energy being E of your system, then and you just want to look at what are the states with maximal entropy, then the maximal possible entropy is given by this, which is Boltzmann formula. Okay, this is the microcanonical ensemble. Okay. If you instead want a description like this, where you fix the number of particles, the volume, and the temperature, then you want to maximize the number of possible states. So you want to maximize the entropy, sorry. Condition on the fact that the average energy is fixed. That you don't have exactly all the states have the same energy, but that the average energy is fixed. Okay, so so you want to have a constraint. So in this case, you want to have a constraint where the sum over R of PR times the energy ER is equal to a certain constant. Okay. So if you ask yourself, what is the PR? What are the probability PR which make this thing maximal, subject to this constraint? Then you will find the Boltzmann distribution. You will find so the maximal S over K such that this condition is satisfied will give you PR, which is equal to e to the minus beta ER over sum over R e to the minus beta ER. Okay, this just you take this formula here with the Lagrange multiplier imposing that constraint, another Lagrange multiplier imposing that PR should be normalized, and you solve the maximum problem, and this is what you get. Okay. I mean, it's a very simple calculation. Okay. So this is just to tell you that this is a very important formula which is worth for you to remember and gives you quite in general what is the relation between the entropy and the probability distribution. It also tells you that the entropy only depends on the probability distribution, does not depend on other physical quantities. And that in principle you could derive all of thermodynamics just from this distribution, imposing the appropriate constraints, that either you fix the temperature or you fix the energy. Okay? Yep. No. You always look at, so in the microcanonical ensemble, we are looking at an isolated system. And we are looking at an isolated system, so the energy must be a constant. And if you look at and you have a certain number of states, microstate, which have that given energy. And if you look at what is the distribution of maximal entropy on these possible states, then you get this entropy here. Okay. Now, if instead you have a system which is in equilibrium with a larger system, then the entropy, the energy fluctuates. It changes. And because there are heat exchanges, okay? So you cannot look, your microstate will not be states with a given energy, only a given energy, okay? So what you can do is to look at, but the energy on average will be fixed. Okay, there will be an average energy. Okay, so what you can do is to look at the states of of maximal entropy, such that this constraint is satisfied. Okay. Hmm? So, so from the point of view of thermodynamics, this is what you have found by studying Cournot cycles and the second law of thermodynamics, right? You have found that essentially in all irreversible transformation, there is a function whose differential is dq divided by t, which is a state function, and that in all irreversible transformation, this function increases. Right? Is the consequence of the second law of thermodynamics. Okay. From this, now what I'm telling you is that there is another way of looking at this, just from the point of view of information, or if you want, of uncertainty. Okay. And so what I've told you at the beginning is that we want to derive a thermodynamic description of a macro state, starting from the laws of motion at the microscopic state. Okay, so that there will be a relation between microstate and macro states. Okay, the assumption which we are making is that all microstates are equally likely, so that we have the maximal uncertainty possible on the microstate. You see? So the statement of maximal entropy is that the distribution over the states which are considered with the macro state, on the microstate which is considered the macro state, is the one which encodes the maximal possible uncertainty. Okay? Why is it? Because if we had any information on that some microstate is more probable than some other microstate, then this should be measurable. This should be measurable, and this should come into my definition of a macrostate, because then I may want to study. This should reflect in the physical condition of my system. Okay. So if this is all I know about my system, and all I care about my system, then for me all the microstates which are consistent with this are equally probable. Okay, there is no, and this is maximal entropy. Okay. Okay, so. Okay, so we have seen how to relate the canonical ensemble with physical properties, how to compute thermodynamic properties. So I want to mention other thing is when the volume goes to infinity, so we have discussed the case where the energy, the states of the macroscopic system are discrete and have energy levels ER. But when the volume goes to infinity, the number of states with a given in any energy interval will be very, very large. Okay, so instead of discussing, and sometimes it is better to discuss things taking the energy as a variable rather than the state as an index. So it is useful to introduce the density of states by saying that G of E times BE is the number of states with R with ER in the interval E plus D. Okay? So if I introduce this quantity here, then the probability to find a state with energy E will be proportional to the number of states which have that energy E. Each of these states will have a probability which is proportional to e to the minus beta times the energy. And then this probability should be normalized, so I should have the integral over the energies of G of E times e to the minus beta times E. Okay, so you can discuss the canonical ensemble also in terms of this the density of states. And essentially, I mean, if you think about it, the density of state is what we have been discussing when discussing the microcanonical ensemble. It is exactly the number of states which have energy E, okay, or energy in a small range around E. So so the other thing is that yes, the Helmholtz free energy in this case is minus kT times the log of this integral So you see, this integral is essentially what you have to compute, and from the sometimes it's easier to compute the integral than to compute the density of states. So sometimes, this integral here is called the partition function. So the the partition function in general is the sum over all the states of e to the minus beta times ER. And in this case, the sum of the integral over the energy of G of E times e to the minus beta times the energy. And you see that the partition function is the Laplace transform of the density of states. So mathematically, these two things are related. Okay, let me discuss classical systems, and let's compute the Helmholtz free energy for a classical system. So in a classical system, the state, well, I have in a classical system, so the state R is essentially equal to a specific assignment of all the position and all the momenta of each of the particles. And the energy ER is the Hamiltonian, is given by the Hamiltonian. And so all I need to do is to, in principle, is to compute the partition function, which is just this integral e to the minus beta times h q m p. Okay? Now, for classical system, there are two problems with this formula. One problem is that this is not adimensional. And the second problem is Gibbs Paradox. So, I mean, this has to do with how we relate points in the phase space to states. And we have seen that we cannot naively associate each point in phase space to a different microstate. that there is a volume of phase space which corresponds to a microstate. And also that when we compute the configuration of the systems, we should not distinguish the particles. Okay? So that the correct way to define the partition function is not this one, but is rather this one. This is a volume of V and temperature, and is 1 over n factorial times h to the 3n times this integral. Well, h q and p divided by kt. Okay? So the use of Planck constant to the 3n makes this integral adimensional. It is a number. And this n factorial solves this problem of Gibbs paradox. So that counts states where does not count states where particles are interchanged as different states. Okay, the corrects for the fact that different just states which correspond to permutation between the coordinate between the label of the particles do correspond to the same physical microstate. Okay. Okay, so the recipe for studying the canonical ensemble is just you have to compute this object, and then you take the log. It's just minus kt times the log of this Qn V and T. And then once you have the free energy, then you have everything. Okay. So in the last 5 minutes, let's do as an exercise, derive again the classical ideal gas. So in the ideal gas, if I have a monoatomic ideal gas, then the Hamiltonian is actually just the kinetic energy. So is the sum over all the particles of pi squared divided by 2m. Okay, and m is the mass of the particles. Okay. Now, so when I compute this integral, the integral over the q is very easy because it just gives me the volume to the power n. Okay. And then I have the integral over the momenta. And the integral over the momenta is just d3 n p e to the minus. In terms of the coordinate, I have just an expression which is this one, where PA is the coordinate, is one of the 3 coordinates of one of the n particles. Okay, I'm summing over all the coordinates and all the particles. Okay. Now you see this integral is dp1, dp2, dp, etc., dp3n of something which I can write as e to the minus p1 over 2n times e to the minus p2 over 2n, etc., etc. So I can rearrange all of this in the same integral n times. Okay, so this is n, so v to the n, h to the 3n, n factorial. And then I have one integral which goes from minus infinity to infinity over one coordinate, dpa, of e to the minus pa squared over 2m. And this is to the power 3n. Now this integral is a Gaussian integral which we have done already a couple of times. Sorry, I forgot that there is a kt here, right? I have to divide by kt. There is kt here. So the integral here is just the square root of 2 pi m kt. So this partition function for the classical ideal gas is 2 pi m kt to the 3n over 2. Okay? So this is it. So if you use the Stirling formula for this, you get that this is minus n kt times the log of b divided by h3 times n times 2 pi m kt to the 3 half. And then there is minus 1. Minus 1. Okay? So this is, so I've just taken the log of this and used the Stirling formula for log of n factorial. And this is the A. So for example, you can check that if you compute minus the derivative of A with respect to t as at n and v constant, what do you get? You get two terms. You get one term where you take the derivative here. This is minus nk times all of this. And then you get another term which is minus nkt. But with then you have to take the derivative with respect to this t. Okay. So this is the log of the product of a number of terms. So it's the sum of the log of these terms. Okay, and the only term which contains t is log of t to the 3 over 2. So this yes. So this will give you 3 over 2 divided by t. So this cancels this. And sorry? The minus? This minus here? Ah, okay, yes. So there is a plus here, and there is a plus here, yes. And very good. So, and if you do this this calculation, you will see that you get exactly the same result as the entropy of the ideal gas, which we have computed in the microcanonical ensemble when you substitute the energy with the temperature. Okay? And actually, well, you can see that, say, for example, if you take, if you compute the pressure, which is minus dA dV, you just get n kT divided by V. Just so you get the ideal gas law. And you get all the physics of the ideal gas from this formula. And so this implies that the results which you derive from the canonical ensemble are exactly the same as the result that you derive from the microcanonical ensemble. And so in the next, what we want to see next time is why is this so? Okay. So we want to understand why is it that in general we will get the same result in the canonical ensemble and in the microcanonical ensemble.